Okay, so again, good morning. So I forgot to introduce myself. So I'm Luís Correia. I am with the IST, the University of Lisbon. So let me introduce the first keynote speaker. It's Ted Rappaport. I dare to say that almost he does not need to be introduced, meaning he's a well-known professor in our area with an extensive, very extensive list of publications and work, well known for his work on propagation and other areas. It's really a pleasure for us to have him with us today and listen to his views and his thoughts on 6G and all the stuff that has to do with his conference. So he's the David Lee Ernst Weber Professor at the New York University. And I agreed with him that I would not reading his CV because then I would spend the 45 minutes of the talk reading his CV. So I'll give the floor to Ted. Ted, the floor is yours. Thank you.
Thank you. Thank you very much. Good morning. Thank you, Luis, and thank you all for being here. I want to say a special thanks to Tommy and to Eric and for the team here at Chalmers and to Luis for the invitation to this, my first EuCNC. And I've known Mati for years and have wanted to go to the 6G summit that he has and never could make it. So here I get both in one shot. So I'm really grateful to the organizers and to you, Mati. Excited to talk with you today about what I see that's likely to happen in 6G. And so I've got a lot of material, but there's really just two main themes. One is, what can we expect? And perhaps not surprising, I think we're going to go higher in frequency above the FR2 and 3GPP up to sub-terahertz. Also, I'll talk a little bit about upper midband, which is gaining a lot of traction. And then how do we make sure we make wireless sustainable? In fact, we're going to have a sustainable lunch today, I'm told, where we do smart reuse of fresh fruit in a special cake. So I think Europe's ahead of the US in terms of sustainability. So when you see some of the math on some of the new ideas I have in how to make sure we design wireless with proper and efficient energy consumption and less wasted power, think of our lunch today. And then I'll conclude. But first, I want to talk about this idea of moving to greater bandwidth. If you look at every generation of cellular from the first to today's fifth generation cellular, you see a huge step up in channel bandwidth each time. But safety and sustainability are really going to become so important to our industry, the way it is in the auto industry and the way it is in so many other parts of society. I think the wireless industry, our field, the ICT field, is going to face much more scrutiny than we ever had. And we started to see a hint of that in the rollout of 5G, and I'll talk about that a little more in my talk. If you look at the history of wireless, all of you know the first four generations were below 3 or 4 gigahertz. We call it sub-6 gigahertz in the 3GPP parlance, where in the radio spectrum, we understood the radio and microwave regions for decades. And then when cellular came out in the 1970s and 1980s, we started to move up to about 1 gigahertz, 900 megahertz, 1.8 gigahertz for PCS back in the early 1990s. And everything for the first four generations of cellular were sub-6 gigahertz. And then, kind of like oil fracking, released new sources of energy, or Moore's Law's increase in transistor capability, we suddenly found this great spectrum by moving above 6 gigahertz. And the reason for that is simple. Getting up to higher carrier frequency provides greater channel bandwidths for a particular fixed percentage around the carrier. So going up higher in frequency gives you for free much wider bandwidths for information transfer. Now, before we went full speed on showing the world that millimeter wave worked, I wanted to make sure it was safe. So I have an appointment in the med school, and with my colleague Chris Collins and graduate student Ting Wu, we studied the entire literature of millimeter wave research. Luckily, there was a lot known about millimeter wave. For decades, people around the world had been using it for diagnostic, surgery, skincare, beauty products. I mean, millimeter wave was well known for weapons in military. So there was a lot of literature and a lot of safety literature and a lot of studies. And so we wanted to make sure before reaching out to the world and showing that millimeter wave could be viable, quite viable for 5G, we wanted to study the world's known literature, and there was a lot out there. And the good news was it was only due to thermal damage of cells or thermal damage of tissue that you could see mutations of atoms and see rogue growth of cells. It was due to heating. There was no evidence, you could find no evidence of non-thermal breakdown of human tissue. Now, the irony of this paper, which came out and was since published in the National Institutes of Health, is that I was diagnosed with acute myeloid leukemia. And by the grace of God, I'm here with you. I have my little brother's DNA. I'm actually 8 years old. I have an 8-year-old immune system. And so a lot of the work I did on 5G and propagation modeling was actually from a hospital bed and chemo brain, and just, I thank God I'm alive. But this has become such an important issue for me, safety, because I believe, I can't prove it, that it was the ionizing radiation that I was exposed to during 1 week in the hospital in October of 2014 due to a heart problem, that all that ionizing radiation created the leukemia. I have no proof, but I went back and got all the medical records. I know I took over 35 millisieverts of radiation in a 1 week period of time, and it's well known that ionizing radiation can create abnormal cell growth and lead to cancer. In fact, if you look at NASA's 5 biggest risks for sending a human to Mars, one of them is galactic radiation that you're exposed to in space. So it's a real worry for me, and I think responsibility for our industry to start looking when we go up to sub-terahertz to just make sure that we go above 100 gigahertz. Let's make sure that there are no biological effects that could be harmful, because I think our industry is going to face a lot of scrutiny. And there's not a lot of research out there about the effects of terahertz. Terahertz is this unknown region. We know a lot about infrared and optical. We know that ultraviolet X-ray and gamma ray, which we're exposed to when we get above the troposphere and we go out into space, all of the radiation from space is ionizing, wavelengths up above visible light, but we know very little about terahertz. Yet, this is where the big bandwidth is, and I'll show in this talk huge opportunities for massive bandwidth. I just want to make sure we know it's safe, so I encourage the research community and government agencies to start looking at studies, animal studies, tissue studies, to make sure as we go higher in frequency there aren't any Heisenberg uncertainty principle problems or anything. We're still 4 orders of magnitude below the frequency of ionizing radiation. That's good news. Millimeter wave was 5 orders of magnitude below. And everything we could find and study said it was very, very safe. I firmly believe that. But as we get closer and closer to optical and ultraviolet, I think it's important we look at that. Now, here's why terahertz will happen and why I think it will be one of the moves to 6G. If you look at 2G, 3G, and 4G, look at the channel bandwidths. We had it 2 gigahertz back in 4G, 20 megahertz channel bandwidths. That's about 1% of a 2 gigahertz carrier frequency. If you look at 5G, say, take a 28 gigahertz carrier frequency, a 1% bandwidth is 280 megahertz, about a 200 megahertz bandwidth, which is what's allocated in a lot of the 5G allocations around the world for FR2 millimeter wave. So if you look at getting up to 1 terahertz carrier frequency, a 1% bandwidth is a 10 gigahertz channel. A 10 gigahertz channel bandwidth, which I'll show is very viable. And you think about a 10 gigahertz channel, you can get a lot of information through that. I'll put that in context in a minute. But the amazing thing is this is very narrow band. And when you're at very narrow band allocations, channel allocations, it's very easy to make antennas do what you want, filters do what you want, keep the phase noise down, build circuits, build radios that perform incredibly well so that this leap in carrier frequency doesn't degrade in other ways. Now, think about that 10 gigahertz bandwidth. What can we do, and where will 6G take us? I want us to look at the human brain for a minute and think about how our brain processes. How do we think? How does our brain work? We have about 100 billion neurons, and each of these neurons are firing asynchronously 200 times per second, and each neuron's connected to about 1,000 others, which means we're processing a speed of 1 billion operations per second. In other words, our brain is computing at 20 petaflops per second, 20,000 terabits per second, if you will. That's each one of us are doing this with our 30-watt brain. And when you think about our storage capability, our neurons are especially storage, so each of the neurons talking to 1,000 others. And so if you assume each neuron's 2 bits, we actually think it's 3 or 4 bits, we have about 100 million megabytes or 100 terabyte very rapid hard drive with 5 millisecond asynchronous access. All of us have that. So 100 terabyte hard drive, we could already buy terabyte hard drives today, and 20,000 terabits per second, that's a fast speed. But look at what $1,000 buys us. If you think about our smartphone today, $1,000 buys a smartphone roughly. And if you look at where we are today, today's technology, we're computing about 1 trillion operations per second in our smartphone with a lot of parallel threads. And if you project out to 2036, we will be, in about 14, 15 years, able to buy at commodity pricing computation comparable to the human brain. That's why you see all this interest in AI and ML today. It's actually predicting and moving towards this fact that we will be, in 15 years, able to buy commodity pricing with computational speeds comparable to a human being. Now, can we remote the human brain? And this is where I think one of the applications of wireless is going, whether we know it or not. The fact is, will this be 6G or 7G? I don't know. But let's go back to that 10 gigahertz RF channel and consider 1024 QAM, which we know is very doable. In fact, we could do 4 times better than that now in the 3GPP standard at 4096. Figure we get some kind of 1,000-time increase somewhere, beyond MIMO, beyond massive MIMO. And actually, I don't need times 1,000, I just need times 250, because I already got 4 for free in the QAM. So it's some new modulation. And if we do that with a 10 gigahertz channel, we can get close to the actual real-time speed of communicating at the rate our brains process, 100 terabytes per second, 1/200th of the human brain. And if we had a 100 gigahertz channel bandwidth, we're at 5% of the human computational speed. Now, I want to make clear that computational speed is not intelligence. I call this wireless cognition, this idea. We developed in 2019, but wireless cognition with raw channel rate is not thinking, but it provides the ability to have computational processing transmitted from remote to the edge to a robotic device to actually be computing at the same speed of what we do today. So what's fascinating is the FCC in 2019, for the first time, opened up channel bandwidths that start to approach this 10 gigahertz bandwidth. In the Spectrum Horizons Act in 2019, FCC Chairman Ajit Pai and the commissioners voted into these 4 new unlicensed bands. They exist today. There are companies making products for these new bands above 100 gigahertz. They have EIRP limits. It's a 10-year license. But what's fascinating, if you look on the bottom left of this slide, is the FCC is using this to seed investment and to see if we can license this for mobile, if we can license this for fixed. So this is actually a playground of sorts to see if we can make this an actual spectrum allocation. And other countries around the world are harmonizing on this. Now, what applications can we do when we start to get up to the terabits or tens of terabits or 100 terabits per second? And if we could actually remote the computational speed of humans. You can think of drones, autonomous cars, robotics, of course. This whole idea of wireless cognition, having surrogates actually thinking or implementing in a robotic fashion in remote areas, exploring, so on. So it's an exciting future. There are a lot of applications. Our smartphone with this wide bandwidth, 5G is the first cellular standard that brings 2 new dimensions we never had in wireless. You think about it, it's really amazing. 2 brand new dimensions. The first dimension is very, very narrow band, narrow time-sliced symbols, very narrow symbols. We have much wider bandwidth, so we should get much smaller symbol duration. So we have great time resolution down to the order of nanoseconds. And then the second thing you get is you start to get higher in frequency, the wavelengths become small, so you now get very small beam widths. You get much better spatial resolution. So we're getting temporal resolution and spatial resolution for free in 5G, and this is the tip of the iceberg for what's going to come in 6G. Now, there's a myth that millimeter wave and frequencies above 6 gigahertz are somehow lossy. And I want to get the facts straight on this. This shows you that the atmospheric absorption, this amazing protection that we have, the great creator gave us this protection of the troposphere, 10 kilometers on down, blocks us from harmful ultraviolet rays and galactic radiation. And that's where people focus on the attenuation and the loss. But if you look at this curve, you study it carefully, that when you're on ground level in typical atmosphere at ground level, look at the curve out to 400 gigahertz. We're only losing 10 dB per kilometer in up to 400 gigahertz. And that's only 1 dB per 100 meter small cell. And all the way out to 900 gigahertz, you can see at 900 gigahertz, down at the troughs, at ground level, we're 100 dB per kilometer lost due to the channel, due to the atmosphere oxygen absorption and so on. But 100 dB per kilometer is only 10 dB per 100 meter small cell. And 10 dB is only a factor of 10, which can be made up with more antenna gain when the wavelength starts becoming smaller than a human freckle. So there's really not that much propagation loss. And in fact, rain, once you get above 70 gigahertz or so, rain is no additional loss factor because the raindrop becomes much larger than the wavelength. So going out to beyond 70, 80, 90 gigahertz, you have flat all the way to 1,000 gigahertz or a terahertz carrier frequency. And what it shows is you could have several kilometers of wireless coverage all the way up to 400, and I claim 900 gigahertz. So 6G will move us towards this new regime where we start to see Moore's law coming to capacity with this new increase in spectrum. So I think 5G's killer app will be kind of the playground and learning about what's going to happen and bringing the technologies for 6G. And one of the big technologies that's happening is millimeter waves and developing the semiconductors and the knowledge and the antennas and the design tools, but also small cells. Countries around the world are deploying smaller and smaller cells, are enacting legislation to allow smaller base stations, smaller size cells to be deployed. And that's independent of frequency. Small cells are needed whenever you make the channel bandwidth wider, no matter whether you're at 1 gigahertz or 10 gigahertz or 100 gigahertz. So the Small Cell Act and the movement to small cells and the use of multiple antennas, MIMO, massive MIMO, will allow us to be able to support and engineer these move to higher frequencies and higher bandwidths. Now, one of the things that's caught a lot of traction lately, and I saw it at ICC in Rome last week, is this move to midband. And 5G Americas did a study on the midband spectrum in the US, and the FCC chairwoman, Jessica Rosenworcel, actually last year at the Mobile World Congress kind of started this move towards opening up the 7 to 15 gigahertz range. There's a lot of hope that we can get that spectrum at the World Radio Conference in UAE at the end of this year. It's going to be mainly satellite focused, but there's an opportunity for the wireless industry to get upper midband spectrum. And you can see other FCC commissioners also are focusing on this move above 95 gigahertz, including terahertz. So you see governments kind of aligning to this move to wider and wider bandwidth. It's just a natural evolution of every generation of cellular. So I think we'll expect that for 6G. One of the interesting things, though, is when you start to worry about how will midband, upper midband work, because there's not a lot known about the spectrum at, say, 16 gigahertz. I say that's an easy problem, nothing to worry about. If you look at the knowledge at 28, 73, and 140 gigahertz and go backwards to 15 or 16 gigahertz, you can really extrapolate. And what you see on this graph on the right is that as you go higher in frequency, the partitions, the walls, the obstructions, they become more lossy. So if you go lower in frequency, they become less lossy. You'll see this theme again and again. But the beauty of millimeter wave and terahertz and why it will work, and there are a lot of good talks at this conference I've seen, is that the mathematics show, I've already hopefully proven to you that the channel itself, the atmosphere, is not going to be a big factor up to 400 gigahertz. So once you remove the atmosphere and you start looking at the transmitter to receiver, what you see is that double directional channels using a directional transmitter and receiver antenna, the math shows you overcome free space loss and you way overcome any atmospheric loss. You totally overcome it. Look at equation 3. The received power for a given distance, for a given fixed physical area of antenna at transmitter and antenna at receiver, that is, keep the area fixed, go up in frequency, that means you give each antenna more gain, but keep the physical area fixed in your handset. Equation 3 shows that you get more power received at the receiver, not less. It's actually more power efficient to operate at higher frequencies. You get less consumption of energy per bit by moving higher in carrier frequency. Now, we've done a tremendous amount of work over the last 10 years plus at NYU, measuring indoor, outdoor. We have rotatable gimbals. We've published a lot. Some of you have probably seen the work. But I really admire the students. They really are like explorers going out into these environments and measuring these new frequencies. And what we found over the last 12, 13 years is really remarkable. I just want to give some highlights, which helps give us an answer about upper midband and going up to 400 gigahertz. And this is the real surprise. It turns out that if you use a simple physics-based reference of 1 meter, free space reference, for the calibrated received power from any transmitter and go into any of these environments, the path loss exponent, or the slope of received power or received power loss versus distance, is virtually identical over every frequency, 28, 73, 140. Here you can see that an omnidirectional path loss model in an indoor hotspot, NYU wireless lab space and offices, has a path loss exponent of 1.42. That is 14.2 dB per decade. That's better than the 2.0 or 20 dB per decade free space because of the waveguiding effect bouncing off the walls, off the floors, and so on. It doesn't matter what frequency band you're in. It's virtually the same model. And even in non-line of sight. In non-line of sight, it's 2.66, 26.6 dB per decade. At any of these bands, 28, 73, 142. The big difference in all these frequencies is simply what happens in that first meter, the dispersion of the radiated power out to 1 meter. This is really good news for wireless engineering. It means that things look to be pretty frequency indifferent. And that means the cellular system designs that are built for 5G, the small cells that are built for 5G, will inherently be the infrastructure which allows us to use the higher frequencies at 6G and 7G. The one difference, though, that you would expect is that as you go higher in frequency, higher in carrier frequency, from millimeter wave to sub-terahertz, you start to lose the diversity, you lose some multipath, you lose some of the weaker energy, and you are getting only more of the highlights of the strong signal components. You can see here for omnidirectional and omnidirectional non-line of sight, line of sight, that as you move to the right, you start to have a smaller average number of spatial directions in which you receive energy. Similarly, you lose time delay spread. That is, you lose time dispersion as you go higher in frequency simply because of the path loss and the less ability for energy to come back through multiple reflections and blockage and so on. the bottom line is there's still diversity even up to 140 gigahertz. And when you go outdoors, you find amazingly the same thing. We went outdoors over the last 12, 13 years in the streets of New York, Brooklyn, in many different environments, trying to emulate what small cells will look like in the future. And these are recent measurements at 140 gigahertz. And again, we find the same thing going all over campus. And here's the beauty of working in a university environment that's not undergoing a lot of construction. We were able to, over a 10-year period, go to the same transmitter and receiver locations on the NYU Brooklyn campus over a 10-year period and recreate the exact same transmitter receiver locations to get roughly the same measurement locations at different frequencies. And you are able to then understand how the physical environment impacts the propagation at different frequencies. And again, we found the same thing. And this is even adding some work we did in Texas at 38 gigahertz. It turns out that the path loss exponent, or the power lost, the coverage, is really independent of frequency. If we reference to a physically based 1 meter free space model based on Harold Free's lambda squared over 4 pi d squared formula. So this is really good news. And this is what some of the actual measurements look like. We can get diversity, so we can use adaptive antennas to exploit the energy and create a link. And similarly, like we saw in indoor, as you go higher in frequency, you start to reduce the diversity. So you get down to about, you can see 1.9, so about 2 average angle of arrival clusters, directions, discrete directions where energy is coming from. The beauty of millimeter wave and sub-terahertz is that polarization works virtually flawlessly. And I'm going to show you, even in the factory environment, you get amazing cross-polarization discrimination. So even though there's only 2 angular arrival clusters, you use polarization diversity and you get 4 paths. So there's really, it's very nice. You actually have a rank of 4 if there's only 2 paths being made because of polarization diversity. And similarly, the time delay spreads decrease as you go higher in frequency, but there's still multipath. Now, we've done over 1 terabyte of measurements over the last decade, and we've made statistical channel models from all these measurements. We make it available for free. NYU Sim, it's open source. We're on our 4th release, version 4.0. We just put models in to 150 gigahertz from factories and urban microcell and indoor. So you now can use for free an NYU Sim MATLAB-based channel simulator, which will reproduce very realistically the statistics that we've measured over the last decade or so. And this is useful. A lot of our sponsors, a lot of the industry are using NYU Sim for their own modem design. It has different characteristics, different rank. It's more realistic because it's based on channel measurements. And so this is a very powerful simulator, so you don't have to do all the work, that hard work that all these students have done over the years. And what you see is you actually get better performance at millimeter wave and terahertz than what using the 3GPP channel model would give you in terms of bits per second per hertz in hybrid beamforming multi-user scenario. We published that stuff several years ago. But the important thing I want to mention is that if we're going to make sustainable wireless, and sustainability, I believe, really will become a focus for our industry. I think we're going to be in the crosshairs of the press and of society as our industry becomes a bigger consumer of power, is when we make design choices or when we do research, I think we really need to consider the power consumption. You know, digital beamforming is a great idea, it's a great research project, but we need a way to measure and parameterize and characterize the power we give up in providing all the DC power to all the components versus hybrid beamforming. There's a trade-off between energy consumption and performance on the link, and all that has to be integrated. I'm going to talk about that at the end. But this is a tool that you can use, and this is something also that the public's going to be increasingly looking at us for, this idea of safety, not just sustainability, but safety. I want to talk about a terahertz co-sharing spectrum project. But before I do this, I want to ask you, do you remember 5 years ago when the United States weather forecasters were saying that 5G was going to ruin the ability for people to predict the weather? Do any of you remember that? Okay, a few of you do. Let me ask you this. Do you remember about a year ago when the popular press in the U.S. started to report that 5G would cause airplanes to fall? Remember that? Yeah. Okay. They're the same problem. They're a spectrum co-sharing or an adjacent spectrum sharing problem. And the bottom line is interference. In terms of the weather thing, it was 24 gigahertz millimeter wave band starting to be rolled out, and there's 5 satellite channels, these very, very sensitive satellites that have virtually zero noise receivers up circling above space, measuring noise to see if there's water. That is, they're basically radiometers looking for noise. So any energy that gets up into the satellite can cause a false alarm. And so there was the 5G 24 gigahertz spectrum was a few hundred megahertz away, and they were afraid the spectral mask would leak in to one of the 5 bands. Now, I don't know about you, but the weather's half off without any 5G, so I didn't see it doing any big difference. But the issue about the airlines was the new 5G spectrum at 3.4 gigahertz was close to the altimeter frequencies of some plane radars. But this is a big issue because it's one of the big impediments to getting spectrum up at terahertz. I want to show you this. We put a satellite up on a roof of a building at NYU to be a surrogate satellite looking down on Earth. This would be replicating one of those super low noise radiometers that are simply detecting energy. And when you look at the problem of satellites, and satellites have to worry about any emission from Earth because it can look like an interference source. Now remember, we have this great troposphere that protects us. So if we're on a slant path looking on the horizon, that if mobile can keep its energy on the horizon, we're able to really have this great protection, virtually infinite path loss. That is, any energy on the horizon is not going to interfere with the satellite on the horizon. You can see this in the graph. We have thousands of dB of path loss due to the troposphere, due to a long slant path. But if you're going directly above, we only have about 10 kilometers of absorption loss. So looking right above to a satellite with a transmitter aiming at the satellite creates a huge interference problem for satellites. So right now in the US and ITU, and this will be an issue discussed at WRC, I believe, you have a spectrum allocation right now out to 275 gigahertz. We're going to go higher. But there are these restricted bands where satellites are operating and protected, and you can see them in gray. And then we have the green Crow primary, which are spectrum availability bands for where 5G and 6G could go to terahertz. Sub-terahertz. And one of the concerns is there's not a big contiguous spectrum allocation for mobile right now. I mean, it'd be nice if we go up to 200 or 300 gigahertz. If we go up to 300 gigahertz, it'd be nice to have a 25 or 30 gigahertz spectrum allocation to allow carriers to operate, have a couple carriers, three different wireless providers competing and offering service. Right now, that doesn't exist because of all these satellites that operate protected. So we went out and made satellite surrogate measurements. You can see on the right is the satellite receiver looking down. And this was during COVID, of course. And the students went out and they took a transmitter at the street level all around campus at different distances. And they moved the transmitter in every possible direction, every rotating angle. And we, at the receiver up on the roof, looked at every possible angle. And we went to many, many locations. And the only thing we could ever find was when we pointed the transmitter on the ground up and at 20 degrees, and it happened to bounce off a sign, and the receiver at the satellite was able to find it with one particular pointing direction. And this is what you found. We found the line of sight path, which you'd expect to have, because there's, because of the fall off on the beam. Remember, this is not a satellite hundreds of kilometers up. This is, up on a building 70 feet, 30 meters. But this was the only place we could find. And while this is a busy slide, it shows, look at the bottom curves at 0 degrees, 8 degrees, and even 16 degrees. If we can keep the energy below 15 degrees, on Earth, of every base station and mobile, we're able to ensure that we're way below what would even be the noise floor seen by a satellite way up in space. So this is good news. It means we could move to co-sharing if we design our antennas to always be on the ground and always on the horizon where the mobiles are, and to avoid going up in space. I think that'll become more and more of an issue as you see wireless go wider and wider bandwidth start to expand our elbows with other services. Now, our latest measurement campaign has been in factories. We've been in 4 factories in the last year studying 140 gigahertz. And it's really fascinating. I don't have time to talk about it. But what's really amazing is factory at millimeter wave started in Sweden, 2015. So, this is where you were one of the first to look at millimeter wave channels in factory buildings. And we've just done the first work at 142 gigahertz D-band. And what you find out in factories is, of course, there's a lot of reflection, so it's more time diverse than indoor hotspot. There's more time delay, there's more angles of arrival, and there's really a difference between a tall receiver and a small receiver. We studied both a human receiver height, 1.5 meters, and an AGV height at half meter above the floor. And there's a big difference. In fact, let me show you some of the locations. You can see on the far right, that's our low receiver height where it's rotating, looking for energy. And you can see we went into a bunch of different kinds of environments. We just presented this at ICC, so I won't talk about it here, but I will give one result of the many results that we found. And what's really cool is even in the very cluttered environment of the factory, the cross-polarization discrimination is still almost as good as the antenna. That is, as you go higher in frequency, you really preserve the cross-polarization discrimination. And I started my PhD work in factories, and that wasn't the case down at 1.3 gigahertz. You had less cross-polar discrimination. You go higher in frequency, you get much more discrimination, which means you get much more polarization diversity, and you get free rank. Okay. So let me conclude with this part of the talk, and I'm going to end with one other idea. There's a lot of great work that's been done around the world, and all of it seems to be corroborating the idea that millimeter wave and terahertz works. It physically is possible. This satellite terrestrial interference issue, I think, is going to become more and more of an issue in our field. I think it's really a wonderful opportunity, especially when I see here in Europe that there's so much work in non-terrestrial networks. It's not like that in the US. So this conference has been really good for me in opening up my eyes to see that maybe satellites and 5G, 3GPP, maybe that will someday integrate. But right now, they seem to be working at different odds, and certainly for the passive satellites, wireless is very scary. Now, Luis, I want to just take a couple more minutes, and I have a bunch more slides. I'm not going to go over them, but since sustainability is so important, I'd be remiss if I didn't talk about this challenge for all of us, and that is, how are we going to conserve energy, and what are the key performance indicators that we can develop for cellular, for Wi-Fi, for computing? I mean, we can do all this great work with AI and ML, but if the cost to do that computing gives us very little incremental gain, we've cost the planet a lot of energy for a gain in one area that's hurt us in another area. And we don't really have KPIs to understand that. And it's going to be a big deal as we go to 20 to 30% of the global power consumption in our industry. And so I want to set this up. I've been thinking about this for a decade, and we developed something I called the consumption factor and power efficiency factor with a brilliant student, James Murdoch. And what James did is he thought about an IoT device of the future, this simple homodyne transmitter, and he thought, how can I figure out how to build the most power-efficient homodyne transmitter, a tiny little IoT speck of dust. How can I design that most efficiently to use the less power? And it's really a fascinating problem because there's no display, there's no ancillary components, there's no other big power consumption other than getting the signal from the sink to the source or the sink to the radio channel. And what he realized, and I give him a lot of credit, is equation 21, is he figured out that the power consumed of any device, whether it's your laptop or your TV or your cell phone or a mixer or an amplifier, is the power consumed in a communication device is simply the power that's transferred in the signal plus the power that's transferred in the non-signal part that enables that signal being carried, and then it's all other stuff. That is, if you look at figure 4, any communication system, any network, any device, any circuit, any end-to-end system has a source and a sink and components on it that either carry the signal or don't carry the signal. And the total power consumed is simply the superposition of the power of all the non-signal stuff and the power of the signal stuff. And what you find out is this is exactly what Harold Freese did at Bell Labs in 1941 to develop noise figure. Noise figure was developed to figure out how much additive noise is created by devices on a cascade. Our problem as an industry is to figure out how much additive waste is created on components in a cascade. That is, 80 years ago, the enemy of planet Earth was signal-to-noise ratio and trying to build radios. We had vacuum tubes. We didn't have broadband. We didn't have cellular infrastructure. We were trying to listen to them, deep space and short wave. And now we have all this great capability and transistors and semiconductors and base stations. And so now we have to worry about what's the new enemy. The new enemy is, how to make a sustainable future. If you go back and do the exact same math that Harold Freese did for noise figure and noise factor, we did this and we came up with waste factor and waste figure. It's a virtually identical approach, except instead of looking at the, and by the way, Nokia has used this to study their high-altitude platforms to figure out that it was less power costly and more earth-friendly to actually use a repeater than an actual base station in the aerial platform. But we published this just a few months ago. But the bottom line is, if you look at noise factor, we're trying to figure out the things referenced to the input. Because in Harold Freese days, it was energy coming into the antenna being transferred to our detector. So we were interested in what's coming at the input and figuring out what's at the output. Harold Freese could have looked at the output at the detector, but he wanted to look at the antenna because you don't know what's out there. It's just coming into the antenna. Instead, we look at the output power. We refer it to the output. And from this, you can then develop a waste factor, W, which tells you if you know the output power, you multiply it by W, that's the total power consumed. So we have really, I think, the beginning of the first KPI to start looking at how much power is wasted. And I just want to show you, this is noise figure. The same idea can be applied to this idea of waste factor, where the power of the waste factor is a cascade, just like noise figure. You get a waste factor, which is a cascade. So we could start quantifying transmitters or hybrid antennas or mixers with a W, just like we have a noise figure on a spec sheet. Every amplifier or transceiver has a noise figure in its spec sheet. Any receiver you buy has a noise figure. We should start doing that for waste figure because it's very easy to quantify. So 80 years later, we have W, which is waste factor. And all waste factor is, all you need to know is the gain and the efficiency of each device. The gain and the efficiency leads to waste factor. So I'll leave it at that. I'll show you. So I'll just ask you one final question, and I'll end the keynote. So if you have three components, an RF amplifier and a mixer and a baseband amplifier, they have a gain and an efficiency. And with that, you're able to figure out the waste factor for each of those components. So for case 1, choosing these 3 components, you get a waste factor of 4.85 dB. And case 2, you have an amplifier which has a little less efficiency, baseband amplifier with a little more efficiency, you get a waste factor of 5.41 dB. So which design do we want to save the planet? Do you want case 1 or case 2? The answer is case 1. You want the lowest waste factor. Just like noise factor or noise figure, where F equals 0 dB means no additive noise, a waste factor of 0 dB means no wasted power along the signal. So a W of 0 dB is no power is wasted and everything from the source gets delivered to the sink with no waste. So you want the lowest waste factor in order to have the best power efficiency and least waste. I'll leave it at that, and thank you very much. Appreciate it.
Thank you, Ted. Thank you very much. Excellent talk. Thank you. So we have time for a couple of questions. Can you please put up the lights? And so there are microphones around the room. So anyone? Yes, please. Please identify yourself.
Hello, I'm Jean-Laurent Plateau from Tara. Great presentation showing us the future with wider bandwidth and meaning going higher in carrier frequency. So if we jump and go even more in the future, higher in frequency, you end up in the optical domain in the hundreds of terahertz. And there are technology already out there in free space optics. So what's missing in free space optics to be also the future? What should people working on free space optics?
It's a great question, and free space optics works great when there's not the sun. I mean, the bottom line is the biggest noise source is the sun. I mean, it is such an intense noise source, and it can reflect off so many things. That's the big limit to free space optics. It will work great in dark data centers, phenomenal. And I think it's already working there. Tunnels, terrific. But whenever there's any source of light from the sun, which is such a potent radiator, it just can't compete with signal-to-noise ratio.
One more? Yes, please.
I think also inside boxes, we'll see that. I mean, we'll see more of that. Optical interconnect works great as long as you keep the light out.
Yeah, hello, thank you for the talk. So it's also my first time attending you live, as it's your first time in EuCNC. So my name is Ahmed Nimr from TU Dresden. My work is more in the signal processing part. So now when I look at this enormous amount of data rate you're talking about, 100 gigabit per second and more, then it is scary for me for the signal processing. Yeah. So this is the first issue. So when I was talking about sub-terahertz, we just talk about the data rate. But what about the energy consumption? So this is also related to your previous or the last slide. And then the other question is, we have also you mentioned the power efficiency for sub-terahertz. So how you can see that using this sub-terahertz even for the IoT devices?
Yeah, no, that's a great question. And you probably work with a great colleague of mine, Gerhard Fettweiss, if you're at TU Dresden. Look at how the microprocessor world has scaled computing speeds. You know, our clock speeds haven't gone up as much, but the parallel threads have increased orders of magnitudes. We now have dozens or even 100 or so parallel threads computing. So I think the key is parallelizing. That's how our brain works. We parallelize. So that's where I think KPIs like waste factor really come into play. You know, what works best? What's the best way? You can't build ADCs. They're so power hungry if you keep getting them faster and faster. So will 10 in parallel at 1/10 the speed with time slicing work just as well or close to just as well with much less power? I think that's a way we address it. I think we have to parallelize the problem and somehow deal with time slicing and time overlapping in smart ways. And then we have to look at the physics, the actual physics of building the devices. What's the most efficient way? I mean, we think in wireless coherent versus non-coherent. You know, there's 3 dB power penalty to go coherent. What's the cost? What are we spending in energy to get that extra 3 dB in the link. So I think it's an open question, but I think going parallel is going to be the key to that.
Okay, thank you, Ted, once more.
Yeah.
Just a small token of our appreciation. You can keep warm coffee in there. Thank you again. Thank you for coming.
Thanks,
It was a
Luis.
pleasure.
Thanks
Thank
for the
you very much.
invitation.
Thank you.
Take care.